Miguel, and I'll be presenting my 6-minute talk on the Stirling cycle engine. So for background, it was invented by Robert Stirling. He was a Scottish inventor, and he patented his engine in 1816, and his company manufactured engines from 1818 to 1922, and they were typically used for energy generation, electricity generation. So what is the Stirling engine? It is a type of closed-loop external combustion engine that uses the expansion and contraction of a gaseous working fluid, typically helium, to move pistons. So some advantages of this engine is that it has a high thermal efficiency. It has quiet operation because there are no fast, vigorous moving parts, and there's no combustion that happens during this. Low emissions, so it's good for the environment. You can use a variety of external heat sources. It doesn't require a lot of maintenance and has a large lifespan, and also has smooth power generation. Some disadvantages is for the size and weight, it does not produce a lot of power. It has a slow response time, so anything that has rapid fluctuations in power, it's not going to do well. The cost, to have your high thermal efficiency, you need quality materials and you need a lot of precision engineering, which costs a lot. You have limited high temperature materials, low power density, and it takes a while for it to start up. So there are typically 3 different types of the Stirling engines. You have the alpha, beta, and gamma. So all of them have pistons. Only the beta and gamma have a displacer. All of them have expansion space, compression space, a regenerator, which is just a porous material that helps with the heat transfer between working gas and external heat sources, which improves your thermal efficiency. You also have your hot side heat exchanger and your cold side heat exchanger. So I'm going to be using the alpha type to explain the cycle. So for your generator, in this case it's going to be your wire mesh, and from phase 1 to 2 you have some heat entering the system, which is going to cause isothermal expansion, and then from 2 to 3 you have constant volume heat removal, and then from 2 to 3 you have heat leaving the system causing isothermal compression. And then finally, 4 to 1, you have a constant volume heating of the system. So some equations, you have your pressure, which is in kPa, you have your volume in meters cubed, specific volume in meters cubed over kilograms, and you have your temperature in kelvins. And in this case, your R is not your universal gas constant, but it is your gas constant of your working fluid, which is joules over kilograms, moles, Kelvin. Some other important equations are your heat from phase 1 to 2. It's equal to R times Tc, ln over V2 over V1. For the phase 2 to 3 and 4 to 1, the heat is the specific heat at constant volume times the hot side minus cold side temperature. For the heat from 3 to 4, your R times TH ln V2 over V1, and then finally your thermal efficiency is equal to 1 minus the cold temperature over the hot temperature times 100 to get a percent. And then applications include automotive engines, electrical vehicles, marine engines, and this is mostly due to the quiet operation, and solar power generation and nuclear power. Those are my references.